In this video, we're going to differentiate the cosec function. Now the cosec function is the reciprocal of the sine function, so cosec theta is equal to 1 upon sine theta. We're going to use the same arguments that we've used in previous videos. We have a little triangle here with the angle of theta. Now in this instance, we're going to keep this height at a value of 1. And we're going to move this point here around to this point here. So we can see here that this height here will always remain the same. And you can see this point moving round about the circle, and you can see that the height here, which is this line in white, always remains at a height of 1. Now that means that if this is a height of 1, then we can write this length here as cotangent of theta. And we can see that from here. We know that the cotangent of theta is equal to cos theta upon sine theta, but the value of our sine theta here is just a value of 1. So that's just going to then say that the cotangent of theta is just equal to the cos of theta. So this length here is the cos of theta, and it is also the cotangent of theta, whenever this height here remains fixed at 1. So that means that if we wanted to find this length here, then we're going to have the square of the 1 and the square of the cot theta, and then we take the square root of it. Now, if you were to work through that little identity, then this length here is going to be a length of cosec theta. So this in effect is the line that we're interested in, and we're interested in how this line changes as we move round the circle. Now we can see here that this line changes here, and it changes by an amount delta theta, which will give us the blue line. So we're interested in this little change here. So let's zoom in, and then we will add in the details for our little similar triangle. So you can see here that as this delta theta tends towards 0, then our little chord here in white is going to tend towards the tangent. And when it tends towards the tangent, the little triangle that we have here is going to head towards the similar triangle that we have here. And again, we use the same arguments that we've used in previous videos. If this is the angle theta and this is the length cos theta, then our little chord here is going to be given by cosec theta delta theta. So we have one length here of our little triangle. Now we know that this is a similar triangle, and this here is our right angle. So it means that this length here is equivalent to this length here. And the small length here is equivalent to this length here. So it means that if this is a value of 1, which in effect is going to be our cosec theta, then in order for the triangles to remain similar, then this height here must be the cosec theta times the cot theta. So that is, if this here is a cosec theta, this here must be the cosec theta cot theta. So it means that we've got two values here in our similar triangle. Now we could find this value here by squaring this and taking the square root, and this will give us this distance here, which is cosec squared theta. So we've got all of the sides of our little similar triangle, but the only one that we're actually interested in is the one that changes the length of our cosec line, which is this line here. And you can see it's going to be changed by this amount, cosec theta cot theta. But one thing we have to be careful about here is that it doesn't add on this distance here, it actually subtracts it off. So whenever this point goes round to this point here, we've actually subtracted off this little distance. So what we've ended up with is minus cosec theta cot theta. So when we differentiate our cosec function, we get cosec theta minus cosec theta cot theta. And let's print this out here on the screen. When we differentiate our cosec theta, we get minus cosec theta cot theta. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.